you can ask me by writing on the chat box, and also you can use your microphone if you prefer. I hope all of you are well. So yes, on Tuesday, Tuesday we did 3 examples on one sample testing of hypothesis. So today I'm going to do more examples. So let's begin. So let me see if I can get this working. Sure. All right, here we are. So this is my writing pad. All right, hopefully it will work better today. Okay. So today I think I did 3 examples on Tuesday. So let's start with example number 4. So all these examples are on testing of hypothesis when you have one sample, right? And consider testing right? So this is example 4, where so the question is to find alpha and beta. Can you read my writing, guys? Okay. So this is so let's start with alpha first. So remember, alpha is the probability of type 1 error. Okay, which is the probability of rejecting the null hypothesis when it is true, which is mu equal to mu 0. So in this example, we are testing for the population mean mu equal to some constant mu0 versus mu greater than mu0. And we have a random sample from a normal population with parameters population mean mu and population variance sigma squared, which is assumed to be known. Okay. Okay, so this will be equal to the probability that root of n times x bar minus mu0 divided by sigma greater than k Okay, guys. Now, I think I told you a long time ago, I think that if you have a random sample from a normal population, one thing you should know is that x bar, the sample mean, has a normal distribution with parameters mu and variance sigma squared by n, right? Okay, this is a fact, right? I think I proved this. Well, I'm not sure if I proved it, but this is the property I stated when I talked about the normal distribution, and this implies that x bar minus mu has a normal distribution with parameters 0 and variance sigma squared by n, right? And which implies that root of n divided by sigma times x bar minus mu has a normal distribution with parameters 0 and 1, right? So these are things you should know from what we learned before, right? Okay, so therefore, because we are assuming that mu is equal to mu0, therefore, what you have above must be a standard normal distribution with parameter greater than k. Sorry, with the variable greater than k. Do you follow what I'm saying? Because that's because we are assuming that mu is equal. We are conditioning on the fact that the population mean is equal to mu0, right? And this you can write as 1 minus the probability that is less than equal to k, okay? And this you can write as phi, okay? Well, so what we have shown, is the following. We have shown that alpha, the probability of type 1 error, is 1 minus phi at k. All right, you follow me? Do you have any questions so far on what I have done? Let me know. Please, you can talk or you can type on the chat box. Okay, now the next thing we need to work out is the beta. Okay, so to find beta, which is the probability of type 2 error, right? Remember, it is defined as the probability of accepting H0 when H1 is true, which is mu greater than mu0. Okay, and this we can write as, excuse me, this you can write as 1 minus the probability of, oh, we don't need to do, okay, let me erase this. Accepting H0 is the opposite of rejecting H0. So you can write this as the probability that root of n times x bar minus mu0 divided by sigma is less than or equal to k, given that mu is greater than mu0. Okay, you follow me, right? Because the accepting H0, as I said, is the opposite of rejecting H0. Right? Okay, and now I'm going to do a trick. Because the true population mean, we are conditioning on the fact that the true population mean is greater than mu0, so it's not equal to mu0. So what I'm going to do is the following. I'm going to change the mu0 to mu. So in place of mu0, I'm gonna put a mu, right? And because of that, I need to add a mu. Okay. All right, guys. So this becomes, you see what I've done? I have replaced mu0 by mu, so I have to add a mu and keep the mu0, right? Now you have basically two terms here. You have this term and you have this term, right? So I'm going to take the second term to the right hand side. So you have root of n x bar minus mu divided by sigma. That's on the left hand side. Now the rest, I'm going to take it to the right hand side. So it will become root of n mu minus mu0 divided by sigma, given mu is greater than mu0. Do you follow what I've done? I've taken the second term in brackets to the right hand side, right? So that's what you get. Okay. Now this, okay, because of the same argument I made earlier. So if you go back to what I talked about here in the red box, all right. Because of the same argument, okay, we can say that this guy here must have a standard normal distribution, parameter 0 and 1. Okay, that's because of the same argument in the red box, and this, the probability that n01 must be equal to phi. Phi is the CDF of the standard normal at k minus root of n all right. So that completes the argument. So just to summarize, your beta, the type 2 error probability, is equal to phi at k minus all right. So that completes example 4. All right, guys. Do you have any questions, guys? Okay, Augustus. Yeah, I'm still confused why. All right. Okay, that's the reason for that is you need to really. Okay, let me go back here. The reason for that, for this argument in the red box, is something that we learned about way back. And you should go back to the course website. This is a property that I talked about a long time ago, that if you have a random sample if you have a random sample from a normal population, then X bar, the sample mean, has a normal distribution with parameters mu and variance sigma squared by n. So this is a fact. This is a fact that I stated a long time ago when I talked about the normal distribution. So that implies that X bar minus mu must have a normal with zero mean and variance sigma squared by n. Right, and that implies that root of n by sigma of X bar minus mu must have a standard normal. All right, is that clear, guys, or not? I hope it's better now. Thank you, guys. Thank you. Any other questions, guys? Please use the chat box. Hello, guys. Do you have any other questions you'd like to ask me? Please feel free. All right, so sorry. Somebody used the chat box and I can't read it. Can't read the chat box. I don't know why. Okay, good. All right, so let's do another example. Maybe, yeah. All right, let's try some other examples, that more difficult ones. So give me a second. So example 5. Okay, so this is example 5, or the next one. All the examples I'm doing so far are on one sample testing of hypothesis. Next week we will talk about two sample testing of hypothesis. Okay. All right. So here, suppose suppose X is a geometric distribution with parameter P, right? So X, and we want to test, the null hypothesis that P is equal to 0.1, okay, versus the alternative that P equal to 0.2, okay? Suppose you reject H0 if X is less than or equal to 5, okay? And the question is to find alpha and beta. Okay, so we have a data that has a normal geometric distribution with parameter P. We are testing for P equal to 0.1 versus P equal to 0.2. And the rejection rule is that X is less than or equal to 5. Okay, so let's see how we can do this. All right, let's start with alpha first. Alpha, remember, is the probability of rejecting the null hypothesis when it is true. So it is P equal to 0.1. Okay, so good, thank you. So this means this is the same as the probability of x being less than or equal to 5 when p is 0.1, sorry, right? Okay, guys, so this you can write as, if x is less than, remember the geometric variable takes values 1, 2, 3 up to infinity. So if x is less than or equal to 5, then it can take the values from 1 to 5. Okay, so x can be any value from 1 to 5 from p equal to 0.1. All right, so this will be and the probability that x equal to I when p equal to 0.1, I'm sure all of you know that is 0.1, sorry, is p times 1 minus p just a minute. Yeah, 1 minus p to the power I minus 1. Okay, so this is the probability mass function of a geometric variable. So in other words, this you can write as 0.1 times 0.9 to the power I minus 1. Okay, guys, is that clear? So just to summarize, so alpha is equal to 0.1 divided by so let me put this in a box. Okay, so this is the value for alpha. Now similarly you can find the beta. Remember, beta is the probability of type 2 error, right? So it's the probability of accepting the null hypothesis when H1 is true, which is p equal to 0.2. All right, so this is the probability. Now, accepting H0 is the reverse of rejecting H0. So it's going to be the probability that x greater than 5 given that p equal to 0.2. Okay. So this is the same as saying that 1 minus the probability that x is less than or equal to 5 equal to 0.2, right? And this you can write as 1 minus the sum okay, right? And finally you can write this as 1 minus 0.1 times from 1 to 5 of 0.9 to the power I minus, sorry, not point, oh, sorry, I'm sorry. It's not point because we changed now. This should be 0.2 and this should be 0.8. Okay, so the conclusion conclusion is the following, that beta should be equal to 1 minus 0.2 times so this is, let me put this in a box. All right, guys, any questions on this, guys? Please let me know. Hello, guys, talk to me, please. Are you okay? You have any questions on the two examples I did so far? No? Yes? No? Okay. So let me do I'm trying to find another example I can do. Just give me a sec. Oh, okay, I found an example. Just give me one minute. Okay. I mean, all the examples we've done so far are on work, except the last one. So this is example. This is example. Oh, sorry. What am I doing? Example 6. Okay. In this example, I'm going to look at something which is not the population mean or the population variance, right? So suppose okay, and we want to um, Right, so this is the question. So you have a random sample from a normal distribution with parameters mu and sigma squared. We are testing for sigma equal to sigma 0 versus sigma greater than sigma 0. With h0 rejected by s squared, it's a sample variance, is greater than a constant k. And we want to find alpha, and beta. Okay. So let's see how we can do this. So let's do the alpha part first. So alpha is this is the alpha part, okay? The probability of rejecting when it is true, right? So this will be the probability that s squared is a sample variance greater than k, given that sigma equal to sigma 0. Now I'm using the sample, the unbiased version of the sample variance, which is, I'm sure you know. Do you guys remember the unbiased version? It's going to be 1 divided by n minus 1 times the sum from 1 to n of xi minus x bar squared greater than k, given that sigma equal to sigma 0. Okay, so this is the unbiased version of the sample variance. You probably recall this from some time ago. Okay, now this, you can write this as the probability that the sum okay, and now I'm going to do something which I think might ring a bell to you. I'm going to divide both sides of this inequality by sigma 0 squared. Right. Now, let me ask you, do you know something about this guy here? Does it ring a bell to you guys? The thing inside the box. We talked about it in the class when I talked about the Kaska distribution. Do you remember what it is? Okay, so do you guys remember this or no? Come on, guys, talk to me. This guy, you should look at the notes. You should look at my notes on Kaska distribution. This guy here, given that sigma equal to sigma 0, this guy must have a Kaska distribution with n minus 1 degree of freedom. Right? That's because of, let me write it down. Maybe just C notes see my notes on chi-square distribution. Right. Okay. So this becomes, you can write this as 1 minus the probability that the chi-square n minus 1 is less than or equal to n minus 1 k divided by sigma 0 squared. Okay, so this will mean this is 1 minus the CDF of chi-square n minus 1 at n minus 1 k divided by sigma 0 squared. All right, so just to summarize what we have done so far, we have proved that alpha, the type 1 error, is equal to 1 minus the CDF of a chi-squared variable at n minus 1 k divided by sigma 0 squared. Right? So this is the first part. Right? Somebody asked me a question, I can't see it. Hello. I saw somebody asking me a question, but all of a sudden disappeared. Who? Is this clear to everybody or no? Hello, guys. Talk to me.
I wrote the question in the chat.
Yes. Yeah. What was it? I can't read it.
How do we know that the variance follows the chi-square distribution? Is it stated somewhere, or is it just by some kind of calculation?
It is stated in my handwritten notes and also in the printed notes. It is stated, sir. Yeah, it is stated there. If you look at my notes under the chi-square distribution, you will see that. Hello? Are you okay?
Okay, so this is for all variance, like 1 over sigma squared times the variance.
Yeah, the 1 over sigma squared times the sum of xi minus x bar squared has a chi-square distribution with n minus 1 degree of freedom. That's a fact if xi follow a normal distribution, which is the case here. That's only, yeah, it's only true if xi follow the normal distribution. Just Stammer, are you okay? Hello? Any other questions, guys? Please let me know. So that's alpha. All right. Now the second part of this question is we need to find beta. Beta is the probability of type 2 error. Which is the probability of accepting the null hypothesis when the alternative is true. Well, the alternative in our, so if you look at the question here, the alternative is sigma greater than sigma 0. Okay, so the alternative is sigma greater than sigma 0. Okay. Now the accept is the opposite of reject. So it's going to be the probability that s squared, the sample variance, is less than or equal to k when sigma is greater than sigma 0. Okay, right? Where s squared is the sample variance, right? Because remember, I said earlier that the rejection rule is when s squared is greater than k. So the acceptance rule will be the opposite of that. Okay. Okay, so this will be, let me write down the formula for S squared, which is 1 over n minus 1 times the sum of xi minus x bars squared less than the constant k when sigma is greater than sigma 0. Okay. All right. Okay. Now I'm gonna take the n minus 1 to the right hand side. So this will be the probability that the sum okay. Okay, and sorry, excuse me, what am I doing? Sorry. Okay, sorry, excuse me. Okay, so this is what we have so far. All right, the next thing I'm going to do is I'm going to divide both sides of the inequality by sigma squared. That's because you see we are conditioning on the fact that the true population standard deviation is greater than sigma 0. So we don't actually know the exact value of the true population standard deviation. So because of that, I'm going to divide both sides by sigma squared, not sigma 0 squared, because sigma 0 squared is no longer the true population standard variance and the true population variance. Hmm. Okay. Okay. Now, using the same argument as I did above, right? Using the same argument, you can say that this probability is the same as the probability that the first term will have, once again, using the same argument, a chi-square distribution with n minus 1 degree of freedom. Okay. Do you guys follow me or no? So it's the same argument I used in the first part of the question, which was to find alpha, right? So now this is equal to the CDF of chi-squared n minus 1 at n minus 1k divided by sigma squared, right? So just to summarize, your beta is the type 2 error probability, is equal to this is the summary of the answer for part 2 of question example 7. Okay. Okay, guys. Are you? So do you have any questions on this example that I've just done? Okay, guys. Come on, please let me know. Do you have any doubts or things that you'd like to tell me? Look, how come I can't read the chat box? I don't know. For some reason, I have problems reading. Okay, so this is example example 2. Sorry, I don't know which example is this. Is it example 6? Yeah, just example 6. I'm gonna give you. Let me see. Okay. I'm gonna give you one more example, right? Which is example 7, but I don't think I'll be able to do it. But I will give this to you as a homework. You can try. You can try this at your own time. Okay. So this is example 7. Okay. Okay. Once again, suppose we have a random sample from a normal distribution with these parameters, right? And consider okay. Consider testing that mu1 equal to mu0 versus the alternative that mu is equal to mu1, where mu1 is less than mu0, right? And reject H0 if root of n times divided by sigma times x bar minus mu0 is less than a constant k, right? All right. Question here is to Wait, oh, I shouldn't write this. Okay. To express n and k, or k and n in terms of alpha and beta. So you're given alpha, remember alpha is the type 1 error and beta is the type 2 error. And the question is to find expressions for k and n is the sample size in terms of alpha and beta. So I would like you to think about this before next time, I mean, before the lecture next week, which is on Tuesday, and see if you can try to do it by yourself. And if you have, if you have problems, of course, you can contact me 24/7. Okay, you can contact me 24/7. All right, now I want to take a 10 minutes break. After that, I will do the example class from 12 to 1, and then we will have another example class from 1 to 2. So in these 2 example classes, I will go through the example sheet 9, which is in the course website. I'm sure you know where it is. All right, so if you go to the course website, you'll be able to see the example sheet 9. So I will see you guys in about 10 minutes from now. Okay. All right, guys. So please join back in about 10 minutes. So okay, thank you.